Okay, folks. Yeah, so let's get started. I'll be traveling today, so I have to record this lecture. So last time, what we discussed is how cache work from a hardware level, right? And in this lecture, we will look at how you could optimize your program to exploit this caching behavior from the CPU perspective and speed up your program by over 100 times. And we are going to use the example of matrix multiplication, which is arguably the most important application today because that's bread and butter at the heart of AI, machine learning, training and inference. Okay. All right. Um, I think the key or the key idea is to exploit locality, right? If you look at the cache, the reason cache works is because your program have a locality, right? Remember, there's temporal locality, spatial locality. Temporal locality says that the data that you use right now likely will be repeatedly used in the future. Spatial locality says that you access the data here, and in the near future, you are going to access the data that are close by, right? In the future. Um, if your program doesn't have locality, then the cache doesn't work. Essentially, you visit data only once, no repeat, then your cache doesn't work, right? So we are going to exploit locality, okay? And yeah, big idea, how do you optimize your program to fit in the cache is that as long as you make your program has better locality, and that locality, based data range you access happen to fit in the cache, then you will get the maximum speed up, right? And we get, again, the cache and memory, the performance discriminant is so large. So that is why we're optimizing it for, okay? And we are essentially, the technique we're going to use is to transform your program to have better locality with respect to the cache, with respect to the cache size, all right? Um, so let's, for example, right, give you some example. If we have an array, a single dimensional array, the type is T and the total number is there's the length is L. Okay. We are going to allocate them sequentially, this array sequentially in the memory. Okay. Now, depending on the type of the array, each element will have different size. If it's a character array, each element will be a single byte. So that if, for example, there are 12 elements, then we'll have 12 bytes. If it's integer array, there are 5 elements. Each element is 4 bytes. In total, they will have 20 bytes. Look like this. Double will have 8 bytes per element. Basically, a floating point number in double precision. And they will be look like this, right? If it's a pointer, this is a pointer array, right? Each pointer is also 64-bit. Right? This because you look at know the star here, right? Let me laser pointer, right? So now this each p is a pointer and it will have 8 bytes, right? Okay. When we have two-dimensional array, which is the matrix later we'll talk about, right? They essentially the underlying compiler will store them, allocate them to store in a one-dimensional array because your entire memory is one-dimensional array, right? If there's basically a chunk of bytes. Okay, so how does it map it to the this two-dimensional array or multi-dimensional array to a one-dimensional address space is using row order, right? So basically, we will store the first row, A00, A01, all the way to A0, C-1, right? The first row, the second row, so on and so forth, right? Okay, so I think we talked about this previously. Okay, now let's look at how a program, in particular array access program, interact with cache. Okay, let's assume a very simple cache. Okay, that the cache has two blocks. There's only one set. Remember, cache they're set associative, right? Assuming there's only one set, and this set have two blocks. Okay, which means that pretty much this is fully associative, but you only have two blocks, right? So any cache line, so any address can go to either one of these. So any block in the memory can go to either block in this cache, right? So that's what it means. Okay. And assume that okay, you can have basically hold 8 bytes per block, right? And also the hardware, let's assume when it needs to replace a cache line or a block, it uses least recently used. All right, that is the assumption we will have throughout this lecture. Okay. Then with these we can answer the question like how many elements per block, how many data structures, all these things, right? But let's look at concrete example. Let's assume, right, these are, you remember, 2 blocks, and we have integer, right? Integer array. And because each block have 8 bytes, so it can hold 2 integers. And we have this loop to iterate through a large array. Okay. Okay, let's maybe assume 4 bytes, for example, at the beginning. All right. Let's calculate the hit and misses, the miss rate and number of misses, right? In total, we'll have 4 accesses, right? That's the matter of how many misses are there, right? Let's go slowly, okay? When we visit, assuming that at the beginning the cache is empty, right? When we visit the first element, we'll bring it in here, right? But because it operates in the block level, granularity, so as we bring in 1 here, we will also bring in the next 4 bytes, which is the next element in the array, into the same block. So that we'll have a miss here. This is a code miss, right? But when we visit the next element, we'll have a hit. Similarly, when we visit the next element 3, we will have a miss, but as a result of that miss, it will bring 3 and 4 into this block, and we'll have, when we have a 4, it's going to be a hit, right? So it will be 50%, right, of miss rate. And at the end, your cache will look like 1, 2, 3, 4. All these 4 elements are in the cache, right? Okay. So let's add an outer loop. We repeat this array access p times, right? Okay. So essentially, we visit once, twice. We go through this entire array once, twice, and all p times, right? So the first iteration, when k equal to 0, when we visit this array, is the exact same behavior talk about, right? So essentially, miss, hit, miss, hit. But at the end of the first iteration of k, our block will contain all these 4 elements, 1, 2, 3, 4. So the next iteration of k, it will be all hit, right? So in total, we will only have 2 misses, right? All from the first iteration of k. And later, doesn't really matter how many, it really depends on p, right? The higher the p is, the miss rate, overall miss rate will be smaller, right? Essentially, it's in this, of course, there this n, right? Essentially, is 1 over 2p or 2 over 4p, right? Why is 4p 4 times p? Because there are 4 accesses, array accesses, for each iteration, for each k, right? So that is the idea. So this is cache friendly. You can't not do better than that because at the beginning is code miss, right? Okay. But remember this, right? I hope that, although that should be easy, right? What we want in the end when it comes from matrix multiplication is we want to simulate this behavior, right? The key thing is that now our cache stores all these data from the inner loop, right? So when we go out for another k, the data is there. We're not evicting any data. So later iterations, they are all there, right? That is the result we want to achieve when we talk about matrix multiplication. right? How do we optimize the program? That is our optimization goal, right? I hope this is clear. Okay. All right. So the lessons for sequential access with reuse, if data fits in the cache, first visit suffer all the misses, but subsequent accesses, they will be all hits, right? Assuming these data fits in the cache, right? But if this array does not fit in the cache, okay, so in this case, let's say there are 8 elements, but our cache can only hold 4 elements, then what happens, right? We will have the first iteration. This is a miss, hit, miss, hit. But once we start to visit the next element, the 5, we will hit a capacity, a limit of the cache. So we have to replace, remember, okay, at this point, right, our thing is 1, 2, 3, 4, right? Actually, let me try to annotate, right? 1, 2, 3, 4, right? This is when we are at here, right, in the very first iteration. Then when we visit this number 5, this element 5, we hit the limit, we need to replace a cache line or a block. We remember we use LRU, least recently used. So we will replace this, and this becomes 5 and 6, right? Similarly, when we visit 7 and 8, we'll replace this block, and it becomes 7 and 8, right? This is what the cache looks like after the first iteration of the outer loop, right? When we visit this A from the beginning to the end one time, right? But then when we go to the next iteration of K, we will start all over again. We'll start from 1, right? So it is miss, so we'll basically replace these with 1 and 2, right? 1 and 2, and replace these with 3 and 4, and only to replace these again with the 5 and 6, with these again with 7 and 8, right? Exactly same behavior as the first iteration. So as a result, every single iteration, we suffer half of the elements that are missing. Okay, so what is the point? Get rid of these. The point is that you look at this program, it's basically the same program as the previous slide, where we have a very low hit ratio, except that the only difference that the cache size now doesn't fit, right? Does not hold, this array does not fit in the cache. So our miss rate suddenly drops raises significantly. Our performance will drop significantly, right? Again, the lesson is that if you have an array look like this, whether you could optimize it, reorder the operations so that we basically have the cache behavior as a previous slide. We visit do the computation or a small amount of data again, so they fit in the cache. We significantly reduce the number of misses. Okay, clear? Right, 50% versus whatever that arbitrary low, 1 over 2p, right? Okay. Okay. Now, if we have a 2-dimensional array, right? We have 2-dimensional array, basically, we go from the first row and then go through the second row, right? I need to erase these. All right. So in this case, what is the cache and misses, right? The first element is hit, this is miss, this is hit, this is miss. Because once you go to the 5, we'll replace the first cache line, contains 1, 2. So it's a hit, miss, right? So I won't draw it. If you're not clear, you can pause here, go slow, draw it on the cache, and you will have this, right? So basically, in this case, we'll have 50%, right? 1 hit, miss, hit, miss, hit, miss, hit, miss. So it's 50%. Okay. So yeah, that is basically this one, right? But previously, this assumed we are visiting this array in a row order. Okay. What if we visit in a column order? Okay, first, why do we even care about column order? Well, remember matrix multiplication, you are basically multiplying one row of the first matrix with a column of the second matrix. So your access pattern of the second matrix is column order, right? So that is why we discussed this, right? Let's assume we visit this two-dimensional array in a column order, right? It's going to be 1, 5, 2, 6, 3, 7, 4, 8, right? What is the miss hidden race pattern? Well, when you say 1, 2, right? We will have 1 and 2. When we visit, sorry, 1, right? We'll have 1 and 2 here, right? I'll go to use a pen, I'll go a little bit slower, right? 1, 2, right? And the next element we'll have 5, 6. We will visit 5, sorry. As a result, we bring in the next element, 5, 6, right? And then next time we visit 2, we'll have a hit. We visit 6, we'll have a hit. And we visit 3, then we'll remove this cache line, right? This become 3, 7. So this is a hit. Sorry, this is a miss, miss. This is hard to use. Hit, hit, miss, miss, hit, hit, right? Okay, so that's 50%. Okay, but I think if you're sharp enough, you will realize that the reason we have these hits is because actually our array is small enough, right? For example, if we have more dimension here, more rows here, as we further move on, we'll replace this 1 and 2, then we will not have a hit here. In other words, the reason we have a hit the 2 here is because by the time we start to visit the second column, okay, this data, this element was still in the cache, was not replaced. But once we have one more row, it's no longer the case. Okay. So that's basically this example, right? Erase all these, right? When we visit the first element, 1, 2, 5, 6. So it is miss. 5 is miss. And then next we visit the 9. As a result, we will kick out this, right? And this becomes 9 and 10. So this is a miss, right? And then the next we visit element 13. So it's 13, 14. This is a miss, right? But now when we go back again to the second column, we have a 2 here, right? It is a miss, right? It is a miss. So as a result, we'll basically bring in 1 and 2 again, okay? By the way, it's not 2 and 3 because the cache line is always in the block granularity. So the block contains 2 is the same block that contains 1, right? They will bring back 1 and 2, right? You see what I mean? Okay. And then the next one, 6, it is a miss again, but we will replace this with 5 and 6. And this will miss again, so on and so forth, right? So as a result, 100%. When we visit a large enough two-dimensional array in a column-oriented order, we will have 100% miss. All the accesses are misses, right? Okay, it's 100% miss rate. Very bad. Okay, but you could see that in the previous, as long as your array is smaller, we have 50%. It's not great, but at least better, right? Okay, and remember that when you have, if your miss rate is 50% with 100%, the performance implication is huge, right? Because now you are converting 50% of your memory accesses from 100 cycle to only 3 cycles. All right. Okay. All right. Let me fix these. So the implication for this one, I hope that you can already clearly see, is that we could just change if you can, right? Depends on the computation, but typically you can do it. This two-dimensional array, when you want to do some computation on every single element, instead of using column order, using row order is much better, right? At least you will reduce half of the misses. But actually later we'll see you can do much better, but at least the lesson is that row order is better than column order. This essentially is to change a column order access pattern into a row order access pattern. Okay. All right. Okay. So now we can start to discuss matrix multiplication. All right. What is matrix multiplication? Well, matrix multiplication look like this. All right. So we have a two-dimensional array A and B. Okay. So we are go through each row, the first, let's say, the first row of A and the first column of B, we multiply each element one by one in this order, right? So the code look like this. This for the ith row in A and jth column in B, we multiply every single element. So in this case, 1 multiplied by 17, 2, 21, 3, 25, 4, 29, so on and so forth. And then after the first one, we go to the first row and the next column, right? We basically multiply 1, 18, 2, 22, so on and so forth, right? Okay. So this is matrix multiplication, all right? And now obviously there's a result. There's also, I'm not showing the result. The result is also a two-dimensional array, right? That stores the result, okay? Let's look at the cache behavior, okay? Let's assume these arrays are large, which is in practice what happens, right? These A and B are large. By the way, if A and B are so small that they already fit in the cache, you can stop right now. You can forget about everything we'll discuss next, right? So they don't apply, right? You don't need to optimize anymore, right? But in the real world, you have heard this machine learning arrays super, super large, right? So they don't fit in the cache. Then what is the cache behavior, right? Let's now even assume, okay, for the simplicity's sake, let's forget about the sets, right? Let's just assume your cache is fully associative, because in reality, just because we have large enough set, so when there's 4-way or 8-way associative, when we have enough blocks in a set, really the behavior of a set, kind of this associate, for example, 4-way or 8-way associative cache, the behavior is almost as good as fully associative cache, right? Because there's enough room, enough space within a set that you can basically play with, right? So the discussion from now, let's assume fully associative cache, the behavior is very similar to the real cache, which is not fully associative, right? Okay. So we are using LRU when we replace the cache, right? Let's go slow, analyze the behavior, right? So the very first iteration, outer loop iteration of I, right? We're talking about the first row and the first column, really is these operations, right? These are specific operations. A00 multiplied by B00, in other words, 1 multiplied by 17. A01 multiplied by B10, 2, 21, 3, 25 is this one, and 4 multiplied by 29, right? Let's look at their access pattern, okay? So at the very beginning, for this one, for this element, it's a miss, code miss. It's not cache is empty, right? So we bring in 1 and 2 here, right? Okay. And then we also record time. This time is the timestamp or the cycles or number of visit, the time this element got visited. So we'll use this time for each cache line. So later when we need to evict, we will basically select the least recently used, the last access time, or in other words, right? And then multiply by B00, right, which is the 17. It's a miss. So we'll bring in 17 and 18, right? And the access time is 2. The next one, A10, is this 2. It is a hit, right? Because it's here. It is a hit, and we'll update the access time to the third cycle, right? And then the next one, B10, 21, is a miss. So the access time is 4. A02, which is the 3 element 3, right? It's not there. Code miss. Access time 5. Okay. And B20, right? Okay. B20, what is B20? B20 is this 25, right? It's a miss. And now we are hitting the capacity limit. Everyone thinks full, so we need to evict a block to make room for this 25, 26. Which one do we evict? Least recently used. Which one is least recently used? Well, it is this cache line, right? Because it has the access time is the furthest away, right? In the history. So we'll replace this block, replace it with what? 25, 26, then we update the access time, right? Okay. And then there's the next element, A03 is this 3, right? Again, we have a capacity miss. We need to evict a cache block. We are going to choose the first one. Oh, sorry. Yeah, sorry. Okay. This is a hit, right? Oh, yeah, we are visiting this element 4, right? Not 3. Element 4 is still there, right? So it's a hit. So we will basically update the access time to 7. And the next element, the last element is this 29. It's not there. So it's a capacity miss. We need to evict one. Which one do we evict? The least recently used, 1 and 2. Okay, we need to evict that. But now you should notice, if we somehow could avoid evicting this 1 and 2, then the next iteration, we are going to use the first row and the second column. We are going to use 1 and 2 again. We will have a hit, right? For the next iteration. But now we are going to evict 1 and 2. Okay, we have no choice. We are using LRU. Okay, so we basically evict this and we replace with 29, 27. This is what the cache look like at the end of the first iteration. We have 8 elements, 8 accesses, 2 are hits, 6 are misses. So our miss ratio is 6/8, which is 75%. Right? Okay. You might have the question to say, okay, since if we could change LRU as replacement policy, we can do better, right? You're not wrong. But if you do that, then you are really pigeonholed, tunnel vision, just the optimized for this case, which later we'll see there's a much more effective optimization. Overall, LRU is still the good replacement algorithm that exploit the locality. So you shouldn't think of changing LRU, but rather than changing your program. Okay. All right, let's look at the second iteration. Okay, we are going to visit the first row and the second column. Right? Okay. So we'll have this at this moment, at the beginning of the second iteration, our cache will look like this. Right? What will happen? Okay, in fact, it's the same. You are not gaining anything from the cache. It's exactly the same as the first iteration, but let's go slow. We want to visit the first element is 1, 2, right? It's not there. We have to do a replacement, right? It's a miss. So we will choose this cache line because it is the least recently used. And we will replace it with 1, 2. Okay. This next one, this 18 is not there. We'll choose this one to evict, least recently used, replace 7, 17 and 18. And the next one is a hit because it's 2 is already there. So we only update the access time. B11, that's 22. It's not there, which was this one. And replace it and put it with 21, 22, right? The next one is 3. It's not there. So it's a miss. Next one, 26 not there. We replace a block. It's this block. Okay. And when we talk about whether this 4 is already there, right? It's a hit. And last one is a miss. We'll replace this one too. Okay. Pretty much the same. Okay. Again, 75% of the accesses are misses. Only 25%, 2 out of 8 are hits, right? This repeats, right? This redundant. It basically the next outer loop iteration, you'll take the first row, third column, so on and so forth, right? The overall miss ratio of a naive matrix multiplication is 75%. All right? Okay. So remember that now we haven't even talked about the result cache, right? Cij in this case, right? That is even have more misses because that matrix also don't fit in the cache. So all of these accesses will be basically missed. Okay. So this is a real matrix multiplication look like, right? You have 3 loops, Cij basically equal to this Aik. The Cij equals to, we take every element in the ith row in A and every element in the jth column in B, multiply them together and add to Cij, right? Or assuming Cij at the beginning is initialized as all 0, right? Essentially, this element in C equals to calculate this element in C, we have to take this row, the ith row, and the jth column. All right? Okay. And what is the misses, right? Is pretty much we already basically discussed, right? So the first row for each row, right? There are n accesses. There are n divided by 8. Why n divided by 8? Because let's assume the cache block size is 64 bytes, which is in real cache. What happens, right? The size of the real cache, each block or each cache line, 64 bytes. It can hold 8 doubles, assuming that each element is double, which is when you do ML machine learning in the AI space, the matrix are typically in double, right? So then each cache line can hold 8 doubles, right? And the cache capacity is much smaller than the actual array themselves. So when we visit the first row or each row, okay, we will have n over 8 misses. That's good because when we bring the first element, the next subsequent 7 elements are going to be hits. But it's only because for this matrix, we are accessing in a row-oriented manner. For this B, the second matrix, because we're accessing a column-oriented manner, everything is missed. Right? Okay. So how many misses? Is n divided by 8 plus n, which is 9n over 8 misses. Okay, so this is essentially the first iteration. Okay. At the end of the first iteration, what does our cache hold? Well, our cache will hold something like that, right? So remember, it's row oriented. So for the result cache, so for the result C, right, we'll hold 8 elements starting from the first element, and the last 8 elements in the first row of A, and this block, right? 8 elements wide, the last 8 rows, right? These block of data will be in the cache by the end of the first iteration. right? I hope this is clear, okay? How does it affect our next iteration, right? Our next iteration for the result cache, we can reuse one, right? That's no problem. But then we are not for A, right? We are going to start from the beginning again. We are not going to benefit from this red. Okay, by the way, in this case, the red part is the one in the cache after the first iteration, right? We're not going to benefit when we revisit the first row of A, and we are not going to benefit for the B when we revisit every from the beginning of the column, right? Okay. So as a result, the second iteration, the miss ratio is exactly the same. It's exactly the same as we discussed previously, right? N over 8 misses on A and N misses on B, right? And at the end, the cache will look like this. This red part is what remains in the cache. All right. What is the total misses, right? Every iteration will have 9 N over 8. And how many iterations? We'll have N squared iterations, right? N squared iterations basically to compute every single element in this N by N array in C, right? So we multiply by each iteration and the total N squared. So we have this is the total number of misses. Okay. So that is how much misses are we talking about? That's a significant number of misses. Okay, and that is what we want to optimize for, right? So I hope it's clear. Again, this is just revisit the numbers. I hope by now you remember this by your heart. Okay. So the L1 cache reference is a few nanoseconds, but main memory is 100 nanoseconds, right? So because of this, if we can somehow reduce significant number of misses, if we reduce that, we can speed up our program by 100 times. Okay. How do we do it, right? The idea later we will see is called loop tailing. Okay. We will divide, instead of doing this entire row of a big array with the entire column of another matrix, multiply them all together, we are going to divide them into smaller tiles. It's called a tile, right? So that we reorder the operations so that the operations that fits in the cache can be basically calculated before we move on, all right? Or if you really think about it, right? Essentially, this is the big C, right? This C00, we require all these elements. In this case, they are 4 by 4, right? And all these elements and all these elements, right? Okay. But if we do it naively, we are going to go this order and this order, right? Visit them one by one, okay? But if we can basically reorder them, and then the next C, this one will be the sum of basically the first row and second column, right? But if we can break it apart, right? So the idea is that let's assume this small block fits in the cache with this small block, okay, with this small block, okay? And if we could just do the computation, all the computations involved with this small block and this small block and this small block, okay, we reorder them before we move on to the next block. So the whole point is we reorder these operations that all the computations involve these elements are all finished before we move on. Okay, this is called tiling. This is the idea. So by rewarding these, we can basically transform, essentially the number of operations is still exactly the same, but we will significantly reduce the number of cache misses. Okay, so that is the idea. All right. Okay. So let's take basically a more kind of more concrete, right? C00 equals what? 1 times 15, 2 times 15, 3 times 14, 4 times 13, right? This is this row, this column, right? Okay. But these operations, right? This addition, right? Essentially these four products, we add them together. We don't do it in this particular order. We first compute this. Okay. We compute this part and we compute these parts later. Because why do we compute this part later? This 14 and 13, right? 3 and 3. This, because we are visiting this small tile, these operations involve elements in this small tile and this small tile, right? Okay, we do that later. So we only do these parts because they requires elements from this tile and this tile. And then we move on. We move on to other Cs that requires other elements from these two small tiles. Okay, so that is the idea of reordering. Okay, so, or in other words, this is the program that we will end up with writing. Okay, we will break down these big original only three loop iterations. We will add 3 more loop iterations. Okay, the idea is to break down this big multiplications into a smaller tile where each tile is t by t by size. Okay, t is much smaller than n. Okay, conceptually look like this. This is a small tile, t by t, t by t, t by t. All right, so that we basically, for this small tile, okay, that essentially require, you think about this small tile, like this element requires this row and this column, right? But we further break it down to say this small tile is going to require this sum of the result. We are going to first perform the multiplication from these elements with these elements. And then the second row here, second column here, and all the way to the last column, last row here, and last column here. Right? That is the idea. So we basically, for each tile, we do all these exhaustive computation that requires all the elements here before we move on to the next tile. Okay? Just to be clear. All right. We multiply this and this, right? These are basically as part of the result of the first element. And then the next row and the next column only within this small tile that is part of that is part of this, right? I mean the first row and second column, right? So on and so forth, right? So basically, after this small tile and this small tile, we have the partial result. It's not complete result of every single element involved in C. And then we move on to the next tile, but still this tile, right? The first tile in this ith row, but the second tile in this J1 column, right? And then we basically the first row, first column, first row, second column, so on and so forth. Okay, the whole point is that now this tile, again, they're small enough to fit in the cache so that when we are doing this matrix multiplication during this operation on this tile and this tile, everything, there's only a code basis, right? All the other subsequent ones are going to be hits, right? And the resulting program will look like this. This is essentially these small tiles. And then we basically, after we finish this tile, and this tile, these 3 small tiles, we increment by t. So essentially we are going to the next tile in B, right? Next tile, and then we go to this tile and multiply by these tiles. right? That is the whole idea. During this whole process, all these elements in the result tile are in the cache, right? Okay. So pretty much it look like this, right? We go with this, start from this tile, this tile, this tile, and then we go to after we finish this, we go to this tile, right? This tile, this tile, this tile, right? So on and so forth. Okay. Yeah, so there's animation, right? We go like this. Okay. All right. And then we move on to the next tile. We go like this again, right? So why does tiling work? I hope I already explained to you, right? Because each small tile, we do a lot of revisits in these small tiles, but now all of these are in the cache. Okay. So what is the total miss, right? In each tile, now remember that our tile size is T, right? Within each tile, right? I mean, we only have code misses, okay? So t square minus divided by 8, right? Why is t square divided by 8? Because for each tile is only the first element will be missed, right? For both row and column, right? Okay, this is t square, right? Divided by 8. This is number of misses, right? It's all code miss, right? The initial access. And even with this tile for the B, right? Even if we visit in the column-oriented manner, we basically, in total, there are t square elements, right? It's only the first time is going to be missed, and every one eighth, right? And then the later ones, they are brought in the cache, even though we are going to visit them in a column-oriented order. When we come to the next element in the same cache line, it's still there, right? So this is why it's t squared over 8 number of misses for each tile. Okay, then it's a matter of how many tiles are there, right? It's basically this number of tiles, so this is the total number of misses, right? So essentially in the tiled access, yeah, in total we'll basically have these number of misses, or 1 over 40. Okay, t is reasonably large, right? Versus 9 over 8 times n squared. This kind of misses. All right, so that's basically what we have for the tile analysis, right? Again, the whole point is that you divide it up to small enough and then have a lot of reuse, right? So lastly, the last 1 minute is that how do you do it? You will be doing it in your lab, okay? For this one, you have to really first do the back of envelope calculation, know your cache size to roughly decide on the tile size, and then do some experiment to see fine tune, right? You will observe that once for the T, there's really a cliff, right? If you basically increase the T at some point, the performance will basically improve, keep improving. As soon as you go over the size of T doesn't hold in the cache, there will be big performance drop, right? And that is that tipping point is where the ideal T is, the size of T is. Okay, all right. So yeah, and that is the end of this lecture. And so next Monday we will basically back in first person. Okay, bye bye.